Alright guys, let's continue with number 3. We're looking at a dog food manufacturer who has to cut production costs and wants to use as little aluminum as possible as she constructs these cylindrical cans. Now we're told that the volume of the dog food cans is 600, and then we need to show that h equals 600 over pi x squared. Because there's a 600 in this relationship I need to show, presumably we need to do something with the given volume of 600. Now in the formula package it tells me that the volume of a cylinder is pi r squared h. So our volume is 600. Our radius has been given as an x, and our height has been given as h. So here's an equation that's true, a volume of 600, and we need to isolate h. And let's get h alone, and we'll divide both sides by pi x squared, and now you've shown the required relationship. Moving on to part B, you need to find an expression for the curved surface area of the can. So it tells you that the curved surface area, tells you in the formula package, is 2 pi r h. In our situation, of course, we need it to be entirely in terms of x. So let's change our radius to an x, and let's change the height to this expression that we found in part A of 600 over pi x squared. And that is now entirely in terms of x. It also asks us to simplify our answer. So if you're ever confused about how to multiply a non-fraction by a fraction, just put the non-fraction over 1, and then hopefully you'll remember that we multiply the tops and we multiply the bottoms. And now the pi's are going to cancel, which is nice, and one of the x's is going to cancel, which is also nice. We end up with simply 1200 over x. So 1200 over x is the answer to part I. Part double I, we now need to find an expression for A, the total surface area of the can. Alright, surface area of the total can is going to be the circle on the top and the circle on the bottom, and then the curved lateral area. So the circle on the top and the circle on the bottom, that's 2 pi x squared. And we've already found this nice expression for the lateral area, which is 1200 over x. And we've done part B double I. Let's move on to the next slide for part C. They're asking us to differentiate A in terms of x. I'm just going to need to rewrite it because I can't remember exactly what I had. It was 2 pi x squared plus 1200 over x. I'm going to rewrite that 1200 over x. Let's bring the x up to the top and it becomes an x to the negative 1. Now it's in a form that's ready to differentiate. So A prime, let's begin the differentiation process. The 2 pi is the big coefficient in front of the x squared, so that hangs out in front, and then the x squared differentiates. And the 1200 is the coefficient that hangs out in front, and the x to the negative 1 differentiates. Don't forget to reduce the power by 1, it becomes x to the negative 2. We've now done part C, we've differentiated. I suppose I could simplify, but it doesn't ask me to. But I'm going to anyway, because I'm like that. And we end up with this, if I bring my x to the negative 2 back to the bottom. Part D, I need to find the value of x that makes this area a minimum. Now I know that a minimum will occur where I have a stationary point, and I can see that the slope of my tangent at a minimum is equal to 0. So let's set my derivative equal to 0 and solve. Easiest way to do this is probably going to be with the calculator. So let's create a new graph. Of 4 pi, I can't find my pi, there it is, 4 pi x minus 1200 over x squared. Okay, I'm going to graph this. I may have to adjust my window. Yeah, it looks like I do, I can't see anything there. So let's take a different window that's much bigger. Let's go, say, from negative. Actually, I don't need to put in any negative values for x, do I? Because x represents a radius. How could I ever have a negative radius? So let's just put my x min in at, say, -1. And my x max, I guess maybe it's as big as 20. Let's give 20 a try. And then my y in this situation represents the total surface area, doesn't it? So I can't have a negative surface area. Let's just stick the min at -1. But maybe my surface area is going to be really big, so I'm going to go up to 3,000 just to make sure I'm comfortable. And let's have a look at our function. Oh, I guess I didn't need to go as high as 3,000. I'm a little bit concerned about this. I didn't expect this kind of shape. Let me adjust my window. Maybe I don't need to go as far as 20. Let's go only out to 10. And if I don't need to go up to 3,000, let's try going only to 300. Let's see if I get a better shape. Alright, I'm looking for the place then where my derivative function is equal to 0. That represents the x-intercept, doesn't it? So let's find out this 0 point right here. That will be where the derivative function is equal to 0. So, second calc, and let's find the 0, the place where the derivative function is equal to 0. My left bound can be, say, 4. My right bound might be something like 6. I'm going to guess it happens at 5. In fact, it happens at 4.57. So the value of x that makes a minimum is 4.57. Another way you could have done this problem might have been by going to the original function. Instead of putting in the derivative, perhaps we should have put in the actual original function, which is 2 pi x squared plus 1200 over x. And if we graphed this one, then we could look for the minimum value. Alright, looks like I need to change my window a bit. Let's increase my y max to something bigger. And look, there's the minimum. And so I could graph my original function and find the minimum with second calc minimum, and then left bound, a right bound, and a guess. And once again, it gives me an x value of 4.57. Now, I suppose this is a better way of doing it because it shows us immediately what the minimum total surface area is. That's the corresponding y-coordinate is. If you type 4.57 into your original function, you'll end up getting approximately 394. And so 394 centimeters squared is the minimum total surface area. And it occurs when x is at a radius of 4.57 centimeters. Alright? And on the next part of the video, we'll continue with numbers 4 and 5.